In the last several lectures, we've been finding the zero-input solution of the differential equation. In the case of distinct roots, we were able to write this zero-input solution in terms of the sum of the modes, e to the lambda 1t through e to the lambda nt, where lambda 1 through lambda n were the characteristic values, which were the roots of the characteristic polynomial. We took these characteristic values and we plotted them in the complex plane. But why did we do this? This is the question that I'll attempt to answer in this lecture. To illustrate why the location of characteristic values in the complex plane is important, let's consider a system. This system will have two characteristic values. Lambda 1 is -6 and lambda 2 is -1. We know in this case that the response to initial condition will be the sum of the modes, e to the -6t and e to the -t. What will this response look like? Let's consider the two terms that make up this response. The first term is c1 e to the -6t, which I plot here. Let's now plot the other term, c2 e to the -t. Here it's shown in blue. You'll note that this second term decays much more slowly than the first one because it's e to the -t rather than e to the -6t. Response to the initial conditions, y0, is the sum of both these terms, and I've shown that here in green. This response can be thought of as having two distinct phases in time. In the first phase, the response decays quickly due to the dropping e to the -6t term. Then, the response drops more slowly. The e to the -6t term is almost completely disappeared, and the decay of y0 is due primarily to the e to the -t term, which is much slower. So the location of the characteristic values in the complex plane tell us something about the response to initial conditions. The characteristic value at -6 tells us that the short time behavior will be dictated by the decay e to the -6t. The longer term behavior is due to the response of the mode e to the -t. So the long-term response is dictated by the characteristic value that's at -1. You can see that the locations of the characteristic values in the complex plane tell us a great deal about the response of the system to initial conditions. It tells us a great deal about the behavior that the output will have. This is the reason why we'll commonly plot the characteristic values in the complex plane, because it graphically gives us a great deal of insight into what we expect the system to do.